1. So of course, this one does not exist if n is less than 0. Here. So, undefined x0. Anyway, if this number is less than 1, it's less than 1, then this function is not differentiable at 0. If greater than 1, when n is odd, this is not odd, even, then smooth here. Okay. In the future, you will see the area of this part is an infinite area, but here is a finite area. Okay, so in summary, we have the general power rule. In short, until now, so far we have proved when n is a rational number, then this formula always true. Of course, true means okay, for x is non-zero, but sometimes x0 is also valid. maybe I can scratch like this on. On any open interval that this one is defined. Okay. For example, this case is not differentiable at the 0 because 0, this formula only holds for positive x. And this is an open interval, such that this one is defined. For this one, this function only defined for x is positive and x is negative. I mean the slope, because an origin does not exist. For this one, it's smooth. So this one is not defined at 0. This function only defined on the open interval, the positive rate. Okay, for this one, only define for x is non-zero. So on this open interval, this relation is true. And for this open interval, this relation is also true. Finally, for this one, this function is defined on the largest open interval. So this formula, roughly speaking, the power rule or general power rule is there for this power function. Differentiate this, whose derivative is n times x to n minus 1. But sometimes you have to know if the denominator is even only for positive numbers, which is also an interval. For this one, non-zero. So positive numbers and negative numbers, they are two open rate, two open radius, open intervals. For this one, it's defined everywhere. So it's defined on the largest open interval. Okay. So I think this explanation is very good. This statement covers all cases, in any case. So open is important. open. Sometimes it's very useful, this terminology. Well, how about for arbitrary real number here? For example, pi or square root of 2. Sorry, undefined now. We will define irrational exponents in chapter 6. Chapter 6. And at that time, you can replace this by r. R. Okay. R. So amazing in the natural science. In the nature. In the nature, how to believe, differentiate this, just put this as an coefficient and decrease the exponent by 1. Okay, let's do some examples in this section. Okay, use power rule 6 times x to the 5th. Use power rule, this is 1,000 times x 999. Okay, decrease the exponent by 1. Power rule. So I strongly recommend you do some work. Just repeat what I wrote on the blackboard. Okay. At least you can watch the teaching videos made by your TA. See? This notation was introduced by Leibniz. Use power rule 4 times t cubed. Differentiate the cubic function with respect to r, the r. So again, use power rule 3r squared. Because differentiation operator is a linear operator, we can pull 3 in front of this one times the derivative of this one. Use power rule, we have 4 times x cubed. Again, because differentiation operator is a linear operator, we can write the minus sign in front of dx. Now this is, again, use the a power rule, this is 1. Or use the identity function. This is the identity function whose derivative is 1. Again, the differentiation operator is a linear operator. This is a linear combination of power functions. So this is 8x raised to the 7th power. 60 times x raised to the 4th power. 10 times 3 is 30. X squared. This is a identity function, constant function 0. Finish? Yes.